let's start lecture B by cleaning up a few things from lecture A. First thing I want to clean up is that I want you to believe that with a logistic model for the US population, if I go back to 1790, that no function will do a perfect job. And so instead of doing a fit of the data with a straight line, what I'm doing here is I'm just using mathematics and manipulate to allow myself to change the K, the L, and the P0. And no matter how you fiddle with this, change K, change L, change P0, none of these do a perfect job of trying to fit all the data. Okay, you're going to be off in one way or the other with this logistic model. So if you want to go back to 1790 and include that, you've got to use some fancier model. Okay. So the next thing I want to clean up is the mean value theorem example we did. So again, we were looking at this mean value theorem. If f is continuous on a closed interval and differentiable on the open interval, you might wonder why not differentiable on the closed interval. You could say that, but you can, quote unquote, get away with an open interval, so it's always good to get away with whatever you can get away with. Then there's a number, c, between a and b, where the slope of the tangent is the same as the slope of the secant. And again, with this picture over here, come back to this picture, there could be more than one value of c. In this picture, c1, c2, and c3 are all places with the slope of the tangent. These slopes, the derivative values at c1, c2, and c3 are all the same, and they are all the same as the slope of the secant. In this picture, visual example, there are 3 c's, but in general there might just be 1 c. This would be an example of a graph where there's only one value of c. And our quadratic example coming over to this side of the board is an example where there's only one value of c. I happen to pick a equal to 6 and b equal to, or negative 6 and b equal to 6 here and look at this part of the graph. And my initial calculation, I made a mistake. C ends up being halfway between negative 6 and 6. It ends up being 0. The slope of the tangent line at 0 is the same as the slope of the secant. And they're both equal to 4. With quadratics, c will be halfway between a and b. That doesn't happen with other functions. What's the purpose of this theorem? Well, its main purpose, no joke, is to prove other theorems. Really? Yeah, and that's a good thing. This is powerful to prove many other theorems. That's why mathematicians think of it as the most valuable theorem, is because you can prove so many other theorems. Are those other theorems useful? Yeah, and the first derivative test is useful for optimization problems, to be sure you got a max or a min. There's also that second derivative test. And there are plenty of other theorems. I'm going to show you a few that it's useful for as well, which do have real-life applications. But let's start by using the MVT to prove another theorem called the IFT. What is that? That's the Increasing Function Theorem. We've talked about that before. We did. Before exam 2 even. The hypotheses are the same as the mean value theorem at the start. Suppose f is a nice function. It's continuous on a closed interval and differentiable on the open interval. Then if f prime of x is always positive for all x in the interval from a to b, and that means is an element of or is in, then f must be strictly increasing on the closed interval. If the tangent line always has a positive slope, the graph's got to be going up. Does this really take proof? Yeah, it does. And I'm going to show you some examples, maybe on Friday even, where things that sound true, sound reasonable, are actually false statements. We've actually talked about that kind of thing before too. In fact, we talked about the so-called converse of this theorem being false. If f is increasing, it doesn't mean f prime is always positive, even though that sounds right as well. The example we talked about before was the example f of x equals x cubed. That's a function whose graph is technically always strictly increasing, but its derivative is not always positive. The derivative at 0 is 0. The tangent line here is horizontal. The tangent line is horizontal. The graph looks more and more horizontal the closer you zoom in, but the graph never is exactly horizontal. Very subtle things there, but technically true, and it's enough to say the converse of this statement, even though it sounds reasonable, is false. So how do you prove the increasing function theorem with the mean value theorem? And will you have proof like this on the exam? Well, you will not have to prove from scratch on the exam, but you should understand the proof enough that if I gave you a partial proof, you could fill in blanks or something, or maybe you could give reasons for my steps. So it's definitely worth understanding. I wouldn't have you prove from scratch. It's a complicated proof, more so than the previous one we've done. It's a subtle proof, maybe a better way to phrase that. How do you prove? You start by saying let x1 and x2 be arbitrary elements of the closed interval. I'm trying to prove that f is increasing on the closed interval. And say x1 is less than x2. Now, is that definitely true? Is x1 definitely less than x2? Couldn't it be the other way around? They're just arbitrary symbols anyway, so it doesn't really matter. That's the truth about why it doesn't matter. And because these are arbitrary, our goal is to show that f of x1 must be less than f of x2. You can have functions that are not increasing. Maybe they go up and down. And you could have two numbers, say x1 and x2, where f of x1 is less than f of x2, but the function is not always increasing. It's the fact that x1 and x2 are arbitrary. They can be anything in the interval with x1 less than x2 that allows us to be done when we show that's true. Because if it did go back down like this, if this were the graph, you would be able to find different x1 and x2 where the function values do not satisfy this inequality, like here and here. Because over this interval, the function is decreasing. So it's the fact that they're arbitrary that allows this to be a worthy goal that finishes the proof. Note that f satisfies the hypotheses of the mean value theorem on the entire closed interval, but also on a smaller interval, a smaller closed interval from x1 to x2. Why? It's part of the assumptions of this IFT. We're supposing f is continuous in the closed interval and differentiable in the open interval. So it will definitely be continuous on this interval and differentiable on the open interval from x1 to x2. So what does this mean? It means you can use the mean value theorem. You can apply the mean value theorem to f on this interval. Hence, there is a number c, strictly between x1 and x2. A lot of symbols here. Think carefully with me. Where the slope of the tangent line, f prime of c, is the slope of the secant line between the 2 points. And the interval that we're thinking about. This is not the picture here. The picture is the function is going up. It is increasing. There's some number c between x1 and x2 where the slope of the secant line, slope of the tangent line at that point is equal to the slope of the secant line. Here's the secant line. The tangent line that has the same slope would be right around here. This would be the value of c. Right there. Do some algebra. Multiply both sides of this equation by x2 minus x1. By the way, I'm not dividing by 0 there either, because x1 and x2 are not the same. You can state the conclusion of the mean value theorem that way. And that's a useful way to finish this proof. How? Here it is in a nutshell. What do I know about these two quantities here? Well, f prime of c, based on the statement of the IFT. In particular, this last sentence here. am I assuming if I'm going to prove the I of t? I'm assuming f prime is always positive. So f prime of c must be positive. That's positive. I'm also assuming x1 is less than x2. So this must be positive as well. And we know the product of two positive numbers is positive. Therefore, this must be positive. And this being positive means this is true. This minus that is bigger than 0. This is a bigger number than this is. That's how we finish off the proof here. We're assuming f prime is always positive, so f prime of c is positive. We also are assuming x1 is less than x2, so x2 minus x1 is positive. So just like I said, this difference is positive, which means now we can essentially take this inequality and add f of x1 to both sides. Switch it the other direction and write it that way. And that's what we want to prove. That means f is increasing. So again, this is not something I have you prove from scratch. It's just too subtle. But you should, as you read it, you should understand it well enough that you could fill in blanks, you could give reasons for things. That's something that could come up on exam 3. Other important results. I have to go over this pretty fast. We'll go into more depth on Friday. There are two analogous theorems to the increasing function theorem. We've talked about these before as well, the decreasing function theorem and the constant function theorem, DFT and CFT. That can be proved in an analogous way with the MVT. So the abbreviations. IFT means increasing function theorem. If the derivative is always positive, the function is always going up. DFT is decreasing function theorem. If the derivative is always negative, the function is always going down. And CFT is the constant function theorem. If the derivative is always 0, the function is constant. And that does exclude the greatest integer function as well, because we're only talking about intervals on which the function is continuous. Furthermore, these theorems can be used to prove something called the racetrack principle, which is in the book. I'm not going to go over it today for this lack of time, but you should read it. And I think I may even have you use the theorem on a homework problem. I have not written the homework yet, but it will be out between 2 and 3 today. If I do assign a problem related to using the racetrack principle, I will come up with my own example and write it up, my own example proof for you as well. If you use it, you'll be using it for a proof. And then you just be mimicking my example. You can use the IFT and the DFT to prove the first derivative test. Why? Well, one thing the first derivative test says is that if f prime is positive when x is less than c and negative when x is greater than c, you must have a local max. If f prime is positive over here and negative over here, the function's increasing over here and decreasing over there. It's got to have a max. That's a quick verbal proof of the first derivative test when f prime changes from positive to negative. On the other hand, if f prime changes from negative to positive, the graph's got to be like this. F prime is negative over here, positive over here. F has got to be decreasing, then increasing. It's got to be a low point. Actually, could have. F prime is 0. CFT can often be used in ingenious ways to prove interesting and important facts. Not enough time to actually do this today. Maybe at least one of them on Friday. Example fact 1. This is the fact that two antiderivatives of the same function over a given interval must differ by a constant. This fact is pretty fundamental. I could even call it a theorem. And it's essentially what justifies saying that, for example, the most general antiderivative of x squared is 1/3 x cubed plus an arbitrary constant, c. To know that that's all the possible antiderivatives. C can be anything. That's This example fact justifies that. You take any two antiderivatives and subtract them, you will get a constant. That they are antiderivatives of the same function over a given interval, like the entire real number line with that example. Example fact number 2. The only solutions of this differential equation, dy dx equals y, are functions of this form. These functions, c times e to the x, are the only functions whose derivatives are themselves. That's not what we've talked about so far. We've talked about how these functions do have a derivative equal to themselves. They do solve this differential equation. But how do you know that they're the only functions that do? That there's no others? The constant function theorem can be used to prove that. Another important theorem that we'll talk more about on Friday. It's called the Extreme Value Theorem. This is something you've read about. And I have mentioned this in class, verbally. And it's part of what justifies the global extreme points occurring either at critical points or the endpoints. It's a quiz question. Either way, you'll find this in section 4.2. What we need to do for the last 8 minutes is introduce another subject. Parametric equations and parametric curves. Our last group of applications, again I've said, are some physics applications. This is the application of physics. Parametric equations are useful for modeling motion. Flows, including fluid flows, and modeling data, what are called density curves. Those are our last 3 main applications for the rest of the semester. And we'll start talking about how integrals are relevant for those things on Friday. What are parametric equations and curves? And what are they for? These are ideal for modeling motion, though they do have plenty of other applications. Think about things moving. Balls moving through the air. We've already talked about free fall to some extent. But we could also talk about projectile motion, throw the ball sideways as well. Or a car driving on the road. Or a bug flying through the air. Different kinds of motion. Parametric equations and corresponding curves are the way to model motion. What is a system of parametric equations? It's a system like that, and I couldn't write it in the PowerPoint in the most ideal way. Let me write it on the board in a more ideal way. It's a system of equations. X equals f of t, y equals g of t. X and y depend on t. Often, it's time. That would be the application for motion. A point, xy, is moving through the plane, say, as time goes by. And it might move slow, it might move fast. It depends. The corresponding set of points that you can generate as t varies, which you can write in set builder notation like this. All the points f of t, g of t, such that t varies over some interval, maybe the entire real number line. For example, all real numbers. That set of points would be a curve, called a parametric curve. And you could try to draw the curve by plotting points. Quick example. If x equals negative 2t plus 1 and y equals t plus 2, to plot the parametric curve defined by this system of parametric equations, you can use technology, but you can also plot points. Make a table with 3 columns. Plug in different values for t, like say negative 2, negative 1, 0, 1, 2. Find both x and y based on these 2 equations. Plug in negative 2, negative 1, 0, 1, and 2 into x's equation. Negative 2 times negative 2 is positive 4, plus 1 is positive 5. Negative 2 times negative 1 is positive 2, plus 1 is positive 3. If you plug in the other numbers, you're going to get those. The same thing for y. Negative 2 plus 2 is 0. Negative 1 plus 2 is 1. 0 plus 2 is 2, etc. Now plot these points in an xy plane. These are no longer intervals, these are coordinates. Plot those points. You're going to get something about like this when you plot the points. A line, which shouldn't be so surprising because these are linear functions in t. Though it is a line that's traced out in a certain direction, from right to left as t increases. So you would draw an arrow on top of it, right? Because when t is negative 2, we're here. When t is negative 1, we're here. When t is 0, you're at this point. When t is 1, you're here. When t is 2, you're here. If this is a motion of a point in a plane, say a bug walking on your dinner plate, that bug is moving from right to left. And draw an arrow indicating that. And that line is an example of a parametric curve, though it is straight. On Friday, we want to consider some examples. Straight line motion at a constant speed, which is actually this example. That's motion along a straight line at a constant speed, in fact. Circular motion at a constant speed. Parabolic motion, though it will not be at a constant speed. Where would parabolic motion be useful? That's motion along a parabola, parabolic. That would be useful for projectile motion, throwing the ball, if there were no air resistance, okay? Which is the simplest thing to assume first, even though it's not realistic. And finally, something elliptic motion, motion along an ellipse, also not at a constant speed. These are some applications we're going to do on Friday. So again, what we're going to do on Friday is we'll do these same topics, the same main topics for today, the theorems and the parametric equations and parametric curves. But we will also introduce integrals. And integrals are going to be an essential tool to help us understand motion, for example. Integrals will be an integral tool, okay? All right, see you on Friday.